Okay, hey everyone. So I'm going to give a quick analysis of round A 2022, where I used Rust, and despite messing up for the first half hour or so of the contest, I still managed to get on 74th place. So I was really happy with that on the front page. And using Rust really paid off. I think I might have got time limit exceeded for this last problem if it wasn't for Rust. My particular solution was doing many hundreds of millions of operations and still managed to run in the 20-second time limit, so that was great. And then actually, potentially this one might have failed if I'd used Python as well, just because I potentially could have used recursion, and the recursion depth was potentially up to 1,000,000 deep, and with Python you probably get a recursion maximum recursion depth error. So yeah, without Rust, potentially I would have only solved 2 or 3 problems. So yeah, it really made a difference. For this analysis, I don't think I'll be talking about Rust too much. So if you're looking for a Rust video, I mean, I will go through some of this Rust code, but I'll mostly just be focusing on the logic behind coming up with these solutions and the thought process. But yeah, if you solve some of these questions and you want to know how I approach them, and you just want a kind of simplified version of the overview, then maybe keep watching. So yeah, I'll just go through the problems. So the first problem, speed typing. So yeah, I don't know if I'll just quickly go over this. Is a reasonably straightforward problem. You basically get given 2 strings, and you have to work out if you can delete letters from one string to get the other string. And so you just scan left to right on both of them, and you just greedily match. So we need an I, so we take the first I, and they match, so that's great. So now we need an L. This is an I, so we just skip that, and then we get an L, which is matches. So now we need an O, so we skip this L, and we get this O, and so on. So we just keep going through, just matching up as many letters as we can. And each time we get a match, we go to the next letter in the first string. And if we get to the end of this string, then the answer is just 2, which is the difference in length between the 2 strings. Otherwise, it's impossible. So that's my solution for that. Yeah, so I basically just I used this library that I went over in a previous video for input. Yeah, this one. So I definitely recommend checking out this GitHub. But yeah, so I just got 2 vectors of chars, and I just went through one vector trying to match it up to the other, and counting how many digits weren't matched. Yeah, go to the next problem. So I thought this one was a bit tricky because what did you have to do? You had to add a digit to a number to make it a multiple of 9. So for example, with 5, we can add the digit 4. So we can either get 45 or 54. And both of those are divisible by 9. And so we take 45 because that's smaller. So we have to find the smallest possible multiple of 9 that we can get by adding a digit to these numbers. And I think I had a feeling that the sum of the digits had to sum to 9. And if we look through all of these solutions, the sum of these digits is a multiple of 9. And so it kind of indicated that we could just sum up the digits of each of these numbers and then work out what digit we need to make the new sum a multiple of 9. I'll just go through that quickly. Yeah, but I think it's a bit of an unfair problem. But we needed to do that because there's up to like 100,000 digits or so. So these are big numbers. But yeah, let's say you have the number 273, let's say. Then we can break that down to 200 times, 2 times 100 plus 7 times 10 plus 3 times 1. So this is generally how we break down decimal numbers. And if I want the general case, then I can just go ABC. So digits ABC. So this is the general case for a 3-digit number. And we'll hope that it works for 4-digit numbers and 5-digit numbers and so on. But what we can do here is we can say, instead of 100, we can say that's 99 plus 1. B times 9 plus 1 plus C times, let's say 0 plus 1. And so we can rearrange this to, or we can change, yeah. We can look, 99 is 11 times 9. And, you know, if this was like a 4-digit number, we'd just get 100. We'd have 999, which is 111 times 9, and so on. So it's always a multiple of 9. So we're going to rearrange this to get 9 as a factor. Let's see. So that would be A times 99 plus A plus B times 9 plus B plus C. What's this? Plus C. So that's 9 times 11. I'm just taking 9 out. That just looks proper. So 9 times A plus 9 times B. It's tough, the B looks kind of like a 6. Plus A plus B plus C. So we can make this 9 a common factor. Oops, this should be times 11 times A plus 1 times B plus A plus B plus C. And we want this number to be a multiple of 9. And it's good we know this is a multiple of 9. So if we look at the number line, say you have 9, 18, 27, 36, and so on. And we know that that's just, when we draw part of this number, like this, but that's a multiple of 9. Since it's a multiple of 9, it has to end on one of these multiples of 9. And we want to know what is A plus B plus C. Well, it has, if we want the whole thing to be a multiple of 9, then it has to, this overall sum has to land on a multiple of 9. Like, yeah. So when we add the two together, we're on a multiple of 9. So we know that, yeah, A plus B plus C is this bit here. So we know that this is a multiple of 9. And so then if we kind of worked our way back, you know, going back to the problem, let's say one of these digits was the digits we added, and we remove it. Then we know all of these, since this is a multiple of 9, we know all these digits add to 9. So I guess their sum modulo 9 is equal to 0. And then if we subtract the digit, then I guess we have, let's see how to do that. So let's just say it was A plus B plus X equals percent 9 equals 0. So that's the answer we're looking for, and we want to know what is X. Yeah, we can. Oh, I see. I know. So a plus b equals negative. Yeah, I've kind of forgotten how to do modular maths. It's been 10 years. A plus b would be negative x modulo 9, I guess. So I think the syntax is like this. So yeah, I'll just go to my code for that. So what was this one? So I basically parsed all the characters into U-size numbers. So a vector of U-size numbers. I just sum them up and get modulo 9, and then if the sum is equal to 0, then so this is the digit I'm looking for, x. Right, yeah, x is just 9 minus s. And so x is the digit we're looking to add. So in this example, x would be 4, x would be 3 in this one, and x would be 2 in this one. And because we want the smallest number, we want to find the first digit in the number that's bigger than x. So just go through, and if the digit's bigger than x, then I just insert it there, and we're done. If we never inserted it anywhere, then we just add it to the end. Yeah, and that's that. Let's go to the next problem. Palindrome free strings. So this one, I was stuck for a little while. I think maybe I was trying to make it a palindrome instead of making it palindrome free. So then I went to the last problem, and then I came back to this problem, and then I solved it pretty quickly. But the idea was just to kind of do a depth first search. So we have a string with some question marks in it, and we have to work out, is it possible to make all those question marks 1 or a 0, so that this overall string doesn't contain any palindromes that are bigger than length 5. Okay. So length 5 or more. Okay. So I was going to use dynamic programming, and then I thought I'll just try a depth first search and see if it works, because I kind of had a feeling there might not be any cycles and it might be fast enough. So I basically just scan all the characters, scan the string. If it's a question mark, I just change it to a 2. Otherwise I just have 0 and 1. And so if it's a question mark, I just go to the next character. So I just went from left to right, and if there's no question mark, there's nothing we can do. So if there's no palindrome of length 5 or 6 at the position we're at, so that's what this code here is doing. So there's no palindrome, so it's not bad. Then we can just try going across one to the next character. And if we get to the end of the string, that means we got all the way through the string without needing to have a palindrome, and so it's possible. And we've enumerated all possibilities. Otherwise it would be false. So if it otherwise, if it is a question mark, then we try setting it to a 1. And if it's not bad and we can go to the next character, then we return true. So if it's recursively, if it's palindrome free, one across from where we are. Otherwise, I try a 0 and do the same thing. So that means I'm doing all possibilities 1 and 0. And I just set it back to 2 and return false. So that worked. I'd be pretty hesitant to write this code in Python because I might get a maximum recursion depth. And if I look at the analysis, actually, they did this graph. So they said there's a few observations. The second observation is that this graph only contains 2 cycles and they can't reach each other, so you can't generate a really bad test case. So I was kind of right in my intuition. If I got time limit exceeded, I would have just added memorization to this, so it would have become like a dynamic programming type thing. Yeah, so I was happy to get that one right. And then, yeah, the hard problem is this interesting integers one. So they've got quite a lot of maths, yeah. So I don't know, this is kind of hard to follow. And I don't think realistically you'd do all of this in the contest. But they did do some pseudocode here, which is a little bit more complicated than my solution, but it is a bit faster. It's my solution. So my solution, I just had one kind of short function, but it was slow because I had a new cache for every single test case. So the mine's about 1,000 times slower than what it could be. But luckily Rust is pretty quick and it still managed to pass. So I guess I could go through this quickly. So the question is, let us call an integer interesting if the product of its digits is divisible by the sum of its digits. So you're given 2 integers a and b, and the number of interesting integers between a and b. So I guess they have an example there. So for example, between 451 and 460, you have 451, 453. So you have 5 different possibilities, and so the answer would be 5. And you can see 451, the product of its digits is 20, and the sum of its digits is 10, and 20 is divisible by 10. So it's reasonably simple how my recursive function works, but it's not exactly clear that it's going to pass the time limit, the 20-second time limit. So this runs in about 10 seconds, so it's just fast enough, and it does, yeah, probably many hundreds of millions of operations. But yeah, first of all, if we want the number between a and b, like let's say here's a, here's b, then if we can work out from 0, we need to be able to do from 0 to b. We need to be able to do from 0 to a, because they could be a case. So if we subtract this little interval from the bigger interval, then we are left with this interval here. And so So instead of having f, a, b, we can just have, we can have some function f, a, b equals, well, let's just say h, a, b equals f, b minus f, a minus 1 kind of thing. So really, all we need to know is how many interesting integers are there from 0 to b, or from 0 to a, kind of thing. So I essentially scan a and b, the interval, and I solve for it. And then so I solve for b, and then I solve for a minus 1, and just take the difference. So each time I create a cache, and then I find the digits of the number. So for that, I've just got this method I wrote, which gets the last digit by taking the number modulo 10, and then it truncates the last digit by dividing by 10, and store them to a vector and reverse vector. And yeah, the size of this cache, I guess it gets to about 1 million or so, or maybe less. So I'm recursing with the digits. So I borrow this digits array vector, which means I can't modify it. And I start off at position 0, which means I'm looking at the most significant digit first, because I want all the possibilities that are smaller than or equal to. So if I'm matching the first digit exactly, and I'm currently equal in my recursion, then I need to track if I'm equal or if I'm less. Anyway, I'll show you the code in that. Maybe it'll make sense, maybe it won't. There's some other variables. So basically, if I get to the last digit, and the sum's greater than 0, it means I've used a digit. And I'm keeping track of the product and the sum as I go along. And if the sum divides the product, then I return 1, otherwise I return 0. Then I have this hash. So if I've seen this situation before, then I just return it from cache. So that's memorization. And this is the core logic here. So this is what I should go through. So it's basically just a brute force. So I try every possible digit from 0 to 9. And if I'm currently equal, so all the digits I've processed so far have been equal, and the digit is greater than the ith digit that I'm currently processing, then I break because it's going to be too big. And then the next product is just the current product times the digit. But this is where I had a bug, which I fixed. But if the digit was 0, like leading zeros, they don't count as part of the number. And so if I had a 0 times 1, I get a 0. And so this would be a 0, even though I haven't actually started using any digits yet. So I want to keep the product as 1 until I start using digits, and then the product can go to 0 if I have a 0 digit. And the sum of the digits, I just add the digit to it. And we're equal if we're currently equal and the digit's equal to the current digit, then we remain equal. Otherwise we won't be equal anymore. And yeah, that's pretty much it. So I was lucky this ran in the time limit. Otherwise I was going to try to remove these two from the cache, and I was going to just use one cache for all of the test cases instead of having a new cache for every test case. So I guess I could explain why I thought that this might be fast enough. So yeah, so A and B are up to size 10 to the power of 12, so that's pretty big. kind of indicates, like, you could do the square root of 10 to the 12. So yeah, I won't bother showing that. But basically, how big can this cache get? How many of these can we get? This kind of indicates how many times this will run. One thing that's good is that as I increases, the product and the sum increase. Like, as the sum increases, the product typically increases. And so there's a bit of correlation between these, which reduces the number of possibilities, which is nice. They can be up to 13 digits. I'll just say there's 12 digits. That's more likely. So let's just say there's 12 digits. Then the biggest sum we can get is 9 times 12. So that's 108. And so there's 108 different sums. Then I should write this down. Ops equals test cases times digits times, so this is 12. I should put the number of digits can just be like the length of the number. I'll just not worry about this one. The product, number of products times the number of sums. And to be honest, if the sum is less than 10, or the sum is greater than 100 or something, then so if the sum's really small or really big, then there's not actually that many products we can have. So let's say this is like 80 or something. And we have 20 seconds for a test case. So we need to, this, and I guess this is 100, the number of test cases. And this is 12. So we need to work out this. And this could be pretty big, it could be like millions, which, so if we divide this by 20, the number of seconds equals, then we have ops per second. So if it's a 12-digit number, how many products can we get? So we can have a 1, a 2, a 3, a 4, a 5, a 6, 7, 8, 9, 10. 10 out of 10. So we could have a 0 too, actually. But if we have a 0, then the product will be 0. So it's not that interesting. And if we have a 1 or many 1s, it doesn't really affect the product, so it's not so interesting. And we could have 2 2s. Or we can even have like 3 2s. We could have, up to 12 2s, I guess. So this is just how, like, in my head during the contest, I was just like, oh, okay, it's around 2 to the power of 16 or 18 or something, different possibilities, and so I'll just give this a try and hopefully it should be fast enough. But let's just go through that. So we can either have each of these digits Like let's say we had 156 as our product, as our number. So we have 1 times 5 times 6 as our product. Then let's just say it's 256. Then we have a 1, 0, 0, 1, 1. So each of these possibilities can either be a 1 or a 0. And we have, so it could be like 1, 0, let's go for this. 1, 0, 1, 1, 0. So if we think of all the possible binary strings, then we're going to take care of every single possibility. If we select a 1 here and a 1 here, it means we've got 3 2's kind of thing. So the number of possible binary strings of size 16 is 2 to the power of 16. So 2 to the power of 16 is this. So then we can just go like that. This is how many operations we're doing per second, which is a lot. So it's like, this is going to be pushing Rust. That'll push Rust to the limits. What is that? Yeah, so 300 million operations a second. And given that it did take us about 10 seconds to run, that could be about right, this estimation. This estimation is quite crude because it's not taking into account the times when we could have like 7 or 8 of the same digit. But then if we have a lot of the same digit, then it is actually reducing the number of possibilities a lot. Also, if all of these were switched on, say, then that's 8 times, so like we had 2 2's, 2 3's, 2 4's, 2 5's, and so on, 2 6's. Then we'd actually have, like, if all of these were a 1, then we'd have a 16-digit number, but we know we can only have up to 12 digits. So in some ways we're underestimating, in some ways we're kind of overestimating. But it's just to give us a rough idea. Another way you could do this is, another way to estimate this is, you could say, we'll have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and each digit can occur up to 12 times. So let's just say, just bear with me for a second. I won't bother doing this whole grid. Let's just say this was 12 high. So then it's like, okay, how many 0 digits does our product have? If it's got 0, then we go to the right. If it had like 1, then we go down 1. So it's got 1, 0, and then let's say it's got no 1s and no 2s, but let's say it's got 1, 2, 3s. And then let's say it's got a 5, and so on. So it's got 3 5s, and then eventually we get to the end of the grid. So we have these pathways that go through this grid that can only go down or to the right. So this is another way to estimate like an upper bound. And we know for sure this is an upper bound. The problem with this is if we have two twos, like we have a path that has two twos in it, it's this same thing as having 1, 4. Because 2 times 2 is 4, for example. And so that product will be the same, even though the digits are different. So, so it's actually a bit of an overestimation, quite a big overestimation. So it'd be better to look at prime factors, I guess. But anyway, let's just estimate how many paths are there through this grid. So we have to go left. We have to go to the right, we have to go down. So we have to go, we can go like, let's say right, down, right, down, and so on. So we have right times, we have to go right, let's just say 9 times. Although I said before, 0 and 1 aren't really interesting. So let's just say 8 times. We have to go right 8 times. And let's say we have to go down 12 times. So there's 12 digits. Then the number of different possibilities or paths would be 8 plus 12 factorial. But then some of these are duplicated. If we have like right 1, right 2, for example, like say we go right, down, and we call this right 1, right 2, down 1, let's just say. That's the same thing as right 2, right 1, down 1. So we actually have to divide by, yeah, some of these have kind of the same thing. So we have to divide by 8 factorial. So we have those. And then we have to divide by 12 factorial to get rid of the other ones. So yeah. Factorial. Plus what's that? That's another estimate. So yeah. Anyway, but due to the correlation I mentioned earlier, I mean, we're estimating 300 billion operations or more. But due to that correlation, it's likely going to be less than that. And also, some of the test cases are going to be easy. Maybe instead of 100 hard test cases, it might be 80 hard test cases. So yeah, I basically just submitted that, and I was happy that it passed and that I was using Rust. And yeah, I think that's pretty much it. So I'll provide a link to this gist. Yeah, thanks for watching.